Hello, I'm Phil Schenk. I'm a junior undergraduate at the University of Pittsburgh, working with Dr. Jeremy Levy, and today I will be talking about the effects of writing parameters on electron transport in sketched single-electron transistors at the lanthanum-aluminate strontium titanate interface. So the single-electron transistor, in general terms, is a conductive island or quantum dot separated from source and drain electrodes by two insulating tunnel barriers, shown here in this diagram, as well as a gate that can tune the energy on the dot. Our group has a renewed interest in these devices. We'd like to use them as kind of building blocks for more complex nano devices. They're very good at charge sensing and temperature sensing, which can be useful on a more complex device, as well as kind of stringing them together to form single electron sources and other interesting nano devices. So in 2011, our group published this paper, Sketched Oxide Single Electron Transistor, where they created one of these conductive islands and had some electrodes going to it and an insulating tunnel barrier around. And they observed resonant tunneling between the source and drain in their transport measurements, which is characteristic of a single electron transistor. But we still have some unanswered questions about this system, notably what happens below 16 Kelvin, which was the base of our cryostat at the time. Now we can go much colder than that, so we just want to see what happens, as well as just how to reliably fabricate these devices, because there are a lot of parameters that go into creating one of these dots with our conductive atomic force lithography system. So I will detail that. So this lanthanum aluminate strontium titanate interface I've been talking about, or LaAIO, STO for short, is home to a lot of rich tunable physics. So these two insulating materials, LaAIO and STO, at the center, at the interface, there is actually a conductive two-dimensional electron gas for certain values of thickness of LaAIO. So above 3 unit cells of LaAIO, it becomes conducting, and below that, it just remains insulating. And the interesting part is we can actually tune this metal insulator transition, this two-dimensional electron gas, using an atomic force microscope tip, which I'll talk about in a second. There are also a bunch of other tunable properties. Spin-orbit coupling, superconductivity, and magnetism are all electrically tunable. And we've also observed some interesting electronic interactions, such as electron pairing without superconductivity, and very recently a kind of Pascal conductance series at the LaAIO-STO interface. So to actually make devices at this interface, we start with bulk strontium titanate and a few unit cells of lanthanum aluminate, which is right near that conductive insulating barrier or boundary there, 3 or 4 unit cells. So we deposit some titanium gold interface contacts to kind of make electrical contact with the interface, and then bringing a conductive atomic force microscope tip down to the sample and applying a positive voltage will actually cause water molecules on the surface to dissociate, and then those protons that are left behind will locally gate the interface, causing it to switch from an insulating to a conducting regime. And so we can actually do this very locally with minimum feature size around 2 nanometers, which can make some pretty thin wires. And we can also erase this process, which is very nice. It's reversible. So applying a negative voltage will remove those protons, and then the interface is no longer gated, so we can create tunnel barriers or just erase wires with this technique. And yeah, this requires no physical modification of the interface layer, so it's reversible, and you can use the same sample over and over again, which is very handy and very time-saving. So to make a single electron transistor with this technique, we first bring the tip down to the sample and just draw a wire. Apply a positive tip bias, drag it in a path, and it will create a nanowire at the interface in whatever path we specify. So in this case, just a wire. And we make another one to intersect that. Then we bring the tip to the middle, apply a negative bias, which will erase as shown there. And then applying a shorter positive bias will create a smaller region of conductive two-dimensional electron gas, which is then separated from these leads by effectively tunnel barriers. So this is a conceptually simple way to make a quantum dot and use it as a single electron transistor. So this is conceptually simple, but you can already see that there are a lot of parameters that go into this process that will have a big effect on the transport properties of the quantum dot. So the erasing or writing voltages that you apply while writing this dot matter a lot, and the duration of the pulses, as well as like a bunch of AFM properties. So there's a large parameter space to explore while creating these devices. So in my experiments, we're actually trying to explore this parameter space as well as we can. So we create a series of devices using different erasing voltages and writing voltages on the pulses that I mentioned earlier. So if you remember the schedule of writing the wire, erasing a spot, and writing a dot. And then we automate the lithography process to kind of just run through a bunch of devices, create them all, and measure their transport properties. And we're actually doing room temperature transport measurements because it's much faster than creating a device, cooling it down to base temperature and seeing, okay, well, it actually didn't work, or that's not very interesting. So this saves a lot of time, and I'll go into that room temperature characterization. So while writing the devices, we're taking IV curves across them. So measuring the barrier width, so erasing the wire will create a barrier. And then at room temperature, with a high enough source drain voltage, there's enough energy to overcome that barrier, but we can measure exactly where that happens, and therefore we can characterize the size of this barrier as a function of time. We can watch it evolve over time, and then, so yeah, here we have an IV curve, kind of fit the tangents of that to the x-axis, and then this voltage across here from this dot to this dot is what I'll call the width of the barrier in volts or millivolts. And then once we know enough about these devices from this technique at room temperature, we can cool them down and see how they act in a quantum mechanical regime. So we find that the most sensitive parameters are the pulse voltage of the creating this inner dot. We find a nice sweet spot of around 11 volts here. Above that, it actually becomes too large and just overwrites the wire, kind of intersects with that. And below that, it's too small, and you can't sense any, like it's just a erased wire, no conductance through there. And then, yeah, so this graph here just shows the barrier width as a function of voltage. And you can see these ones are dying off very quickly, just becoming wires, and these ones are not strong enough. So this is the regime we found. And we did the same type of test for the erase pulse, in which case, if you do too large of an erase pulse, you'll again just have no conductance through there, and too small will just leave you with a wire. So that's what we observe in these IV curves at different voltages. So we kind of want to be in this regime. And then once we have these devices, we cool them down, and we observe a very nice Coulomb staircase effect. So this is a resonant tunneling between source and drain. Once the source and drain levels overlap with one of these quantized energy levels on the dot, we'll actually see a path for the electrons to flow through there. So this IV curve shows that. Up here we have kind of the first channel that the electrons can flow through, and then above a certain point we have enough energy that another second channel can go through, so the conductance is twice as, or the current is twice as high. And then we see a third one as well. So in summary, we create single-electron transistors at the LaAIO STO interface using a conductive atomic force lithography technique. We characterize them as quickly as possible at room temperature to be more efficient in sweeping through this parameter space by measuring the IV curve nonlinearity. And then we measure the low temperature and transport properties and observe resonant tunneling and Coulomb staircase.